Good afternoon, sir. Connected, sir, now. Okay, no problem.
Sir, good afternoon, sir. Start చేయమంటారా సార్? Hello.
Yes, ma'am. Yes.
Deepthi. Thank you. Deepthi.
Yes,
Start ma.
Yes. A warm welcome to the respected dignitaries and faculty members. Hope you all are staying safe. Welcome to the short-term training program on research trends in renewable photovoltaic system and its research challenges. Myself, Sridipti, pursuing third year from the Department of EEE from SV Colleges. I take the pleasure of inviting a man of distinction and a fountainhead of illuminating ideas, Dr. K. Sudhi, sir, HOD of EEE Department. Welcome, sir. Now, I consider it a great honor to speak about our chief guest, Kevin K.S. Garu. He is presently working as a managing director, R&D engineer, AB Technologies, Tech Power Solutions, Hoser. Sir also worked as an assistant professor. Sir has total 6 years teaching experience and 4 years industrial experience. He has completed BE in Electrical and Electronics Engineering from CSI Institute of Technology and his MBA from Madras University, Chennai. Sir did his ME in Power Electronics and Drives from Shanmuganathan Engineering College, Pudukottai. Sir has PhD in Electrical Engineering from Government College of Engineering, Tirunelveli. His areas of interest are electrical machines, power electronics, special electrical machines. Sir has published many papers and attended conferences. Sir also got many achievements. Welcome, sir. Now, I would like to hand over the session to Kevin K.S. Garu.
Thank you, ma'am.
Thank you, sir.
Okay, ma'am. I will start the section, ma'am, now. So good afternoon to all. So today I will explain about the vehicle dynamics and the motors and electronic components. So myself Kevin from AB Technologies, Chennai. So actually we have to know initially what is the use of vehicle. So vehicle is used to carry some loads. So for this electric vehicle as well as vehicle, it mainly requires some fuels as well as some tires and some drivers, etc. So actually this image is the basic form of the vehicle, but we know the speed of the vehicle is very low. So that's why we are moving to some advanced vehicle. So a vehicle is used to transporting the pupils as well as goods. So the main components or main parts of the vehicle is, first one is engine, and the second one is battery, then radiator, after that alternator and brakes, etc. The main components of the vehicle is, first one is engine only, and the second one is battery. So battery is used to store the energy, and the engine is used to convert the input fuel into mechanical energy. That means rotation. So conventional system of the basic vehicle is IC engine, internal combustion engine, and the drawback of the IC engine is the pollution wise it's too high, and another one is it can produce only little bit the torque. It cannot deliver maximum torque at minimum speed. That is the drawback of the IC internal combustion engine. So in order to overcome the drawback, first one is pollution, and the second one is cannot attain the maximum torque. So to overcome these two problems, we are moving with the electric vehicle. So this electric vehicle consists of one or two electric motors for propulsion purpose. So for this electric vehicle, so input is we have to give AC as well as DC supply according to the electric motor. So this is the best example for the EV electric vehicle, that is mean electric train. From the DC grid, we can give the 11 kV DC supply. From that supply, that train will work. This is the main block diagram of the EV electric vehicle. So the electric vehicle first consists of engine. Already I told it is used to convert the fuel into mechanical energy. That means speed as well as rotation. Through the mechanical coupling, the tire will move, and the battery it is used to store the energy in the form of electrochemical. And this is the electric vehicle block diagram. So it is a solar based EV. So input is, first one is solar panel. So from the panel, we will get variable DC voltage but we have to give constant output voltage DC voltage to the load. That's why here we are moving with on DC to DC converter, and to track the maximum power, we are using MPPT, maximum power point tracking algorithm, and the DC to DC charger. That means bidirectional converter. This bidirectional converter will work in both the buck as well as boost mode. During the buck mode, the battery will charge, and during the boost mode, the battery will get discharged. Then battery management system, here we have to measure as well as we have to monitor the SOC, state of charge. In detail, I will explain later. And through the grid also, we can get the AC voltage. From the AC voltage, the inverter will convert the, initially it will convert the DC into AC, but in the bidirectional purpose, it will convert AC to DC. We can give this DC voltage also to the battery converter, then the battery will get charged. So this is the general block diagram of the EV, electric vehicle. So the electric vehicle consists of, first one is the solar panel and the DC to DC converter, then one inverter, then we can give the voltage to the grid, as well as we can take the voltage from the grid. So it is a bidirectional operation. The battery management system is used to monitor the battery as well as battery converter. So it is the solar car. Actually, in the EV electric vehicle, we have to choose the motor as very importantly. In the propulsion motor, here I am suggesting some of the DC motor as well as AC motor. First one is the DC series motor, and another one is the DC shunt motor. Then and the last one is the three-phase induction motor. First, we have to know about the working of the DC motor as well as DC shunt as well as DC series motor. The DC shunt as well as DC series motor having the outer part, we can tell it as yoke. It is used to give protection for the machine. And the outer part we can tell it as field system, and the inner part is we can tell it as armature system. Both the field system as well as armature system having windings and that means coil. The coil is made up of copper as well as aluminum. The important thing is copper only. If we provide the DC supply to the DC shunt motor as well as DC series motor, the motor actually it will not run, because for armature, if you provide a DC supply and field system, also if you give the DC supply, the shape of the flux will be a DC shape only. That means a straight line. It's like a railway bridge. So the both the magnetic flux of armature as well as field system, it will not get cut. So to overcome the problem here, we are using commutator. So it is the commutator part. Commutator is made up of copper segments. Commutator is made up of copper segments. That's why we are telling armature slot and teeth. It's like a square shape only. So if you provide the DC current, the commutator will convert into alternating current. That means it's like a square wave only. But we have to give this current to the copper coil. But here commutator also, we know it is made up of copper segments. Coil also made up of copper. So we cannot short circuit these two. So because heavily the short circuit problem will come. So to overcome the drawback, in between we are using carbon brush. So carbon brush is used to collect the current from the commutator and it will use to the winding. Then due to the magnetic flux, back EMF as well as mechanical force, torque will produce, so that the machine will tends to run. In DC shunt motor, here you can think it the commutator, mechanical commutator as well as carbon brush is the additional part only. The weight of the machine will increase and the maintenance problem will come due to the carbon brush. So to overcome this problem, we are going with the next motor, that means induction motor, AC motor. But one of the good advantage of the DC shunt motor is its P-torque curve. If you apply the load, even though if you increase the load, the speed of the motor will not decrease much. So that is the advantage of the DC shunt motor. So we can tell it as to constant speed torque machine. DC shunt motor. It is the one of the advantage, but remaining all are drawbacks only. Very low efficiency compared to AC machines. Lifetime of the machines will be very less only, and efficiency is very low. So many drawbacks are there. So commutator and the carbon brush will increase the maintenance problem. We have to give regular maintenance to the DC motor. So in order to overcome the problem only, we are going to three-phase induction motor. So here you can see it is the commutator. It is the armature, slot and teeth. If you provide the DC current, now it will pass like square wave only. You can tell it as alternating current, change in current. It is the speed torque curve of the DC shunt motor. Here you can see it is the reference speed, but we can expect almost constant speed only in the DC shunt motor. So next one is the three-phase induction motor. So for three-phase induction motor, it's having two main parts. First one is stator and another one is rotor. Stator will not run, but the magnetic flux will run. So here we have to calculate the synchronous speed of the stator first of all. So NS is equal to, we know, 120 F by P, 120 F divided by P. So how the 120 is coming here means total degrees here 360 degree. That means in induction motor stator total angle is 360 degree. That 360 degree is divided into number of phases by 3. So 360 by 3, it will come 120 degree. So 120 into supply frequency of that frequency is touched by number of poles. So 120 F divided by P. It is the magnetic flux speed of the running speed of the stator side. For rotor, actually here we are giving the supply to the stator part only. The rotor having windings, but we will not give additional supply to the rotor. So if you provide AC supply to the stator coil, what will happen? The current will pass through the conductor and the magnetic flux will produce. So this flux is linked with the rotor conductor. So because of the Faraday's first law, whenever the conductor cuts the magnetic flux, an EMF will induced. So it gets induced EMF in the secondary, that means rotor side. Now we know Faraday's second law. Whenever the current carrying conductor cuts the magnetic flux, a mechanical force, torque will produce. So if you give 415 voltage to the stator winding, only 380 voltage will get induced in the rotor side because of the leakage reactance problem. So here the flux, we can fix the flux with the two types. First one is that means leakage flux and useful flux. So the flux passing through the air gap, we can tell it as useful flux, and the flux passing through the unwanted area, we can tell it as leakage flux. So due to the leakage flux, some voltage will get reduced so that the machine will not run at synchronous speed. Ns is equal to 120 F by P. So in the induction motor, slip problem will come. So we know the definition for slip. Slip is equal to Ns minus Nr. That means stator flux speed minus rotor speed. So this difference will make the induction motor speed torque curve with very worst characteristics. That means it will go with negative also. So regenerative braking problem will come. We can utilize the regenerative braking, not a problem. But under motoring mode, it is the waste one only. But one of the advantage of the induction motor is, so it does not need any maintenance. Also, lifetime of the AC motor will be very high compared to the DC motor. So if we club these two motors, we will get the brushless DC motor, BLDC motors. So first we have to know the advantage of the DC shunt motor as well as the three-phase induction motor. In the DC shunt motor, I told the speed torque curve, constant speed torque curve, so that we can utilize the rotor part of the DC shunt motor, and in the stator part of the three-phase induction motor is very good one because it's having symmetrical winding with 120-degree displacement. So we have to combine the three-phase induction motor stator and the DC shunt motor rotor part. But in the rotor part, that means in the DC shunt motor, the rotor having, that means armature having windings. So here the BMBLDC motor consists of the rotor is made up of permanent magnet, so that losses wise it's very less in compared to the normal DC shunt motor as well as the three-phase induction motor. So anyhow, BLDC motor is the combination of the DC shunt motor as well as the three-phase induction motor. So if we combine these two, we will get a brushless DC motor. Once again, I will tell you, the stator part is made up of, it's like a three-phase induction motor, and the rotor part is like a, that means under speed torque curve, it's like a DC shunt motor, but the rotor part is made up of high, that means permanent magnet. So because of this, we can get high torque per inertia ratio and high efficiency. Then low EMI problem, electromagnetic interference problem. Also it needs very less maintenance. So the BLDC motor we can use widely in the aerospace as well as medical equipment production applications. This BLDC motor, brushless DC motor, does not need any mechanical commutator. It requires only electronic commutator. For that also I will explain the reason. So already I told BLDC motor, it is a permanent magnet. Rotor is permanent magnet. So without knowing the position of the rotor, we cannot run the BLDC motor. It's like a three-phase induction motor. We all of them know, for three-phase induction motor, we will apply the sequence with RY, YB, BR. So through one voltage source inverter, 120-degree phase shifting inverter, there we will run with 120-degree displacement. It's like a RY, YB, BR. But in the BLDC motor, we cannot run like that because the rotor is permanent magnet. So here we have to know the rotor position. Without knowing the rotor position, definitely we cannot move the, we cannot run the BLDC motor, brushless DC motor. So for this BLDC motor, the advantage is first one is speed torque curve. Here also it's like a constant speed torque curve machine, like a DC shunt motor only. It does not having any mechanical commutator as well as brush, because it's need only electronic commutator. There is no need of mechanical commutator, so that we can omit the carbon brush, use of carbon brush. Here we can omit it. So it's like, it's a BLDC motor, 24 volt 60 watts BLDC motor. Actually this is the sensor cable. Inside the rotor there are 3 Hall sensors there. It is mounted mechanically with a 60-degree displacement and electrically 120-degree displacement. So from the Hall sensor we can get the rotor position. How it's possible means, initially we will provide 5 voltage DC supply to the 3 Hall sensor HA, HB and HC. So if we give the 5 voltage supply to the Hall sensor, we know magnetic flux will produce definitely. If the rotor conductor nears to the Hall sensor, what will happen? The rotor, that means this Hall sensor flux will cut the rotor conductor, so that an EMF will induced in the Hall sensor. So from the Hall sensor HA and HB, HC, From that we can find the rotor position, because if which sensor gives initially the first signal, we have to know, we can know it near to the Hall sensor, the rotor winding is there. That means rotor pole is there. So according to the rotor position, now we can energize the stator winding. So that's why I'm suggesting BLDC motor is the best example for the EV electric vehicle application. And the speed, maximum speed of the three-phase induction motor, we can achieve 1415 RPM, and in the DC motor we can get 2000 RPM. But for this BLDC motor, it will run up to 3000 RPM. Actually, in the BLDC, the difference between the brushless DC motor as well as PMSM motor, permanent magnet synchronous motor, is according to the rotor forces, that means rotor material and the rotor back EMF. The PMSM having sinusoidal back EMF with 180-degree displacement, and the BLDC motor is 120-degree displacement. We can tell it as trapezoidal back EMF. So BLDC motor having trapezoidal back EMF shape, so that the machine will run up to 3000 RPM, even though our synchronous motor also will run at 1500 RPM only. So for high speed applications, we are going with which one? BLDC motor plus brushless DC motor. So, and another one drawback, without the use of the three-phase inverter, that means electronic commutator, we cannot run the BLDC motor, because already I told, according to the Hall sensor signal only we can run the brushless DC motor. So it is a conventional PV electric vehicle as well as electric pump application. So the same construction we can use it for EV as well as solar pump. So from the solar panel we will get variable voltage. That voltage is given to the converter, DC to DC converter, boost converter. Here you can see the converter having only one inductor and one capacitor, so that we can tell it as a single order low pass filter. Single order low pass filter. So the filter will reduce the ripple contents, and you can see this diode. Actually, it will allow the voltage from PV to the inverter. If any return current comes, means the positive terminal is connected with the cathode, so that we can tell it as reverse biasing. So under reverse biasing condition, the diode will not work. So we can tell it as dV by dt protection as well as snubber protection. So this switch is used to control the output voltage. Later I will explain very clearly. So anyhow, this boost converter will boost the output voltage from the solar panel, and this voltage is given to the three-phase inverter. So from the electronic commutation, that means Hall sensor signal, we can run the motor, we can run the BLDC motor. So here basic MPPT algorithm is P and O as well as incremental conductance algorithm. It's applicable for medium power applications only. We cannot use it for high power applications. So these are the drawback of the conventional BLDC drive system. So from the existing case, totally we are finding unaligned rotor poles. So that means without knowing the rotor position, if you run the BLDC motor, it will increase the losses. The DC to DC converter gain means output voltage divided by input voltage. It must be high. And the highly distorted current will produce the jerk in the speed of the motor. Definitely it will produce jerk. Then choosing the converter. Here actually we have to choose the converter with both buck as well as boost operation. If only buck converter or boost converter, it's not suitable for bidirectional operation as well as BLDC motor applications. So the best one is boost mode compulsorily. And if the converter having buck mode, then we can select that kind of converters. And torque ripples. So if the converter working under discontinuous conduction modes, definitely torque ripples will be very high, because if our input current is continuous, means if current is continuous, definitely we know the torque is directly proportional to current, so that we can expect very less ripple contents in the torque. But if you choose discontinuous conduction mode current conductors or converters, what will happen? Definitely some ripples will be produced in the current, that will affect the torque also. And finally, here we have to choose good speed control technique, otherwise power quality problem will come. So main objective for creating the EV electric vehicle is, first one is we have to construct one good DC to DC converter for improving the efficiency from the solar system. That means we have to track maximum power from the system. So finally, with one optimization technique, we can compare the existing P&O as well as MPPT algorithm. Then one closed loop speed control operation. Actually, if you run the BLDC motor under open loop means only speed feedback I am telling. If you apply the load, what will happen means automatically speed will reduce. But for EV application as well as pump applications, we have to run the motor as constant speed. So that here we have to use one controller, PI controller, proportional plus integral controller. Then we have to reduce the ripple content as well as voltage switching stress. Then finally we have to minimize the torque ripples. So after 1 minute, I will explain the general block diagram of the BMPLDC motor based EV electric vehicle. Okay, I will start the section now. So for EV, it's grid-tied EV electric vehicle. So the solar panel output voltage is given to DC to DC converter, and that DC to DC converter is controlled with the PI, GW or some advanced optimization technique. Then the output voltage is given to the three-phase voltage source inverter. Similarly, here you can see if we having sufficient power from the PV system, at that time we can give the DC voltage to the single phase inverter. From the inverter we can convert this DC voltage into AC, and we can give the AC voltage to the grid. So if we didn't get any power from the solar panel, at that time we can take this DC voltage from the grid and we can give this voltage to inverter, and from the voltage the machine will run. So because of this we can make the electric vehicle as continuous operation. Otherwise, through solar panel you have to use so many number of batteries. So if we increase the number of batteries, the cost will be very high. Also the space requirement also it's too high. So to overcome the problem only we are enabling with the grid-tied operation. So if you take some supply from grid, then no need to use any battery converters. But if you want to store the energy for regular backup, definitely we have to use battery. But this is the simple structure for running the electric vehicle without any usage of batteries. So now I will explain one by one. First one is solar system. So solar system, that means our solar panels will convert the solar energy, sunlight into electricity. First we have to know what is solar system. The conventional energy resources are actually we are generating the power from, first one is thermal power plant and another one is the nuclear power plant. So from the thermal as well as nuclear power plant, the input source is for thermal power plant coal, and the nuclear power plant is uranium. Actually we are depending the uranium from Russia only. So you can think about the transportation cost, it's too high. Also it will produce electrical hazards, heavy pollution contents. Then maintenance, then labor charges, initial investment, then transmission system. So you can totally think it highly, it's pollutionable as well as it's amount wise, money wise, it's too high. So in order to overcome those problems, we are going to renewable energy resources. Under renewable energy resources, the first one is the solar system and another one is the wind energy conversion system. So compared to wind energy conversion system, solar system is the best one because for wind energy conversion system, here we have to use high initial amount. That means, but for PV system, it's not like that. Only space requirement will come, but cost wise compared to the wind energy conversion system, it's very low. So that's why we are choosing solar based system. So actually this is the equivalent circuit of the solar panel. So here actually the solar panel current, it depends on the temperature as well as intensity. The temperatures increases, physically we can tell it as electrons will flow there. It is the materials made up of solar panels. Actually there are two types of materials we can suggest is, first one is silicon dioxide and germanium dioxide. Both SiO2 as well as germanium material having resistance only, that means series resistance and the parallel resistance. So anyhow combinedly we can tell it as resistance, and this is the electrons. So flow of electron we can tell it as current. So it is I into R. This is the way we will get voltage. So I into R is equal to voltage. Once again I will explain this one. From the solar panel we will get variable temperature as well as various intensity. According to that temperature as well as intensity, the flow of electrons will vary. We know the flow of electron is called current. So I into R we will get voltage. So this is the way solar panel will convert the sunlight into electricity. Next it is the IV as well as PV curve. So IV as well as PV curve. From the curve we can see it. If the temperature as well as intensity varies, means definitely power will vary as well as voltage will vary. But we cannot give this variable voltage to the load as well as our EV electric vehicle. Now design of the converters first. Actually for making the motor to run, first we have to fix some DC voltage. So for single phase motors, we have to give 300 volt DC. Then only from that 300 volt DC, we will get 230 volt AC. And the second one is 3-phase motor. For 3-phase motors, we have to maintain 600 voltage DC. So from that 600 volt DC only we can get 415 voltage AC. So if you want to get 300 voltage as well as 600 volt DC, here we have to connect more number of solar panels. So with the 36 cells, seriously connected cells, we will get the 12 volt from the solar panel. Under short circuit condition, maximum voltage we will get 12 volt at 35 degree temperature and 1000 intensity. So 12 volt, it's not enough, but already I told we require 300 voltage. So to make 300 voltage, you have to connect a 25 solar panel in series. If you want 600 voltage DC, here you have to connect 50 number of solar panels. So 50 into 12. At that time also, if temperature as well as intensity varies, you cannot get 300 voltage as well as 600 voltage DC. So to reduce the solar panels, number of panels only, we are going with the boost converter. So it is the first converter, boost converter. And the boost converter having one inductor and one capacitor, so we can tell it as single order low pass filter, and this diode will give dV by dt protection as well as number protection. The energy stored in the inductance is half Li square. So if we give 12 volt, you will get maximum 18 voltages output. So input is 12 volt and we can get the output voltage as 18 volt. So output gain is that means gain of the converter is output voltage divided by input voltage. So that we will get 18 divided by 12. So we can tell it as 1.5, 1 is to 1.5. So it is very, very low. So if we give 12 volt, actually here we have to get 15 volt output, means here you have to turn on the switch with the 75% duty cycle. Under 75% duty cycle only you will get 15 volt. If you maintain 99% as well as 98%, at that time only you will get 17 to 17.5 volt output. That means what I am telling to come means output gain of the converter is very, very low. So it will produce high switching losses as well as switching stress. So here we cannot use boost converter for high power applications. But the advantage of the boost converter is its input current is continuous, so that we can expect very less electromagnetic interference problem as well as torque ripple problems. But these are the drawbacks. Only boost mode is possible. Here we cannot do buck mode. Also another drawback is output content, the ripple content is too high in the output. So to overcome the problem, we are going with the next converter. It is SEBI converter, single-ended primary inductor converter. Actually, this is one of the good converter. So it's having, you can see it's having two inductors, L1, L2. and two capacitors C1 and C2. So we can tell this converter is second order low pass filter. So compared to the boost converter, ripple contents of the output voltage we can expect very low. So then here it's having diode. So this diode will provide dV by dt protection as well as snubber protection. So sub converter also input side the input current is continuous only, but output current is discontinuous. Here you can see the in output side there is no inductor. So in the sub converter input current is continuous and the output current is discontinuous. So next converter will replace this drawback. The gain of the sub converter we can expect up to 1:8, so that we can reduce the number of solar panel as well as number of cost also. So it is the advantages of the sub converter. So sub converter is the single ended primary inductor converter, single ended primary inductor converter. And another one difference between the boost converter and the sub converter, in the boost converter we will use normal inductor, but here in the semiconductor we will use a transformer as inductor. So how it's possible means we know transformer. It is a static device used to transfer the power from one circuit to another circuit without changing any frequency. Both inductor, primary and secondary are both are separated means we can tell it as transformer. But if you connect it in series, that means primary winding and secondary windings are connected in series means now we can tell L1 plus L2 is equal to L. So this is the way we can use the transformer as inductor. So anyhow, the input current is continuous and output voltage gain is 1:8. So this sub converter can work under both boost mode as well as buck mode. If you maintain duty cycle is 0.5, less than 0.5, the converter will give buck operation. If you increase the duty cycle more than 0.5, we can achieve the boost mode of operation. And the next one is the loop converter. Here in the loop converter, you can see input current is discontinuous and in the output side having one inductors. So in the loop converter, input current is discontinuous and the output current is continuous. So if you club the loop converter as well as sub converter, you can maintain both input current also continuous and output current also continuous, so that we can expect a high amount of efficiency. And the next converter is interleaved type converters. So interleaved type converters means with the common DC source, we can connect two converters in series with input side. That means parallel with input side, and in output side, we have to connect it in series. We know if we connect two batteries in series, what will happen? Definitely, both voltages gets added. So 12 plus 12, 24 volt, like that way we will come. Actually the gain of the loop converter almost 1:8 to 1:10 times will come. If we go with interleaved type topology with the common input DC source, we will get nearly 1:18 times gain. So output of the gain will increase with the interleaved converters. So these are the main advantages of the interleaved loop converter. First one is high output gain with very low input voltage, and the second one is there is no reverse polarity problem in buck converter as well as buck boost converter. The polarity problem will come. Polarity problem means if we give the input shape as plus and minus, the output of the converter will become as minus and plus. That is the drawback of the buck boost converter as well as buck converter. And here both input as well as output current will be a continuous one, and we can expect high efficiency and low switching stress as well as losses. Then circuit also we can design very easily. Then we can use transformer as inductor, so that we can omit the EMI problem, electromagnetic interference problem. Then since the converter already it's having inductor as well as capacitor, so no need to use any additional filter circuits. So after 2 minutes, I will explain the proposed system control techniques for DC-DC converters. I will start the control techniques for the converters. So first one is, there are two types of control techniques. First one is MPPT, maximum power point tracking, and another one is the closed loop control technique. So the difference between the MPPT technique and the closed loop control technique. For MPPT technique, we will take the feedback from only input side. That means and for the closed loop control technique, we will take the feedback from the output side. That means output voltage. That is difference between the maximum power point tracking and the closed loop control technique. Actually, under MPPT, first one is the P&O, and it is a very simple algorithm. So this is the algorithm for P&O algorithm. Flowchart for the P&O algorithm pulse. Here you can see the sub converter. Actually, you can let us take the input voltage of the sub converter is 100 volt, and here we have to take 400 voltages output. But already I told the gain of the converter is 1:8. So if you do 100 volt under the inductor, we can get uptake up to 800 volt. So from the 800 volt, here we have to give 400 volt output. So here we have to compare one carrier signal with respect to one the reference signal. So carrier signal is the triangular signal with the 10 kilohertz frequency, and the carrier signal, so carrier is the triangular, and the reference we have to compare with 0.5. That means 1 volt carrier and 0.5 volt reference. So here we will get 50 volt. That means 50% on time and 50% off time. So that duty cycle T is equal to alpha is equal to T by T. So 50% duty cycle will come. So from that 800 voltage with the 50% duty cycle, here we can take how much voltage? 400 voltage. Now let us take our input. Your input is, it's reduced from 100 volt to 75 voltage. At that time also, under the inductor, we can get 600 volt DC. So from the 600 volt DC also, we can give 400 voltage output, but with 0.75 duty cycle. So here we have to increase the duty cycle. That means reference signal from 0.5 to 0.75. This adjustment will do it from the MPPT algorithm as well as the closed loop technique. Anyhow, the purpose of the MPPT algorithm as well as closed loop technique is used to generate the which signal only, reference signal only. So the function of the MPPT as well as closed loop techniques are to generate the PWM pulses only. That means to generate the reference signal only. So first algorithm is already told, P&O algorithm. For P&O algorithm, initially we have to measure the solar panel voltage as well as solar panel current. So for every 10 milliseconds, once we will multiply the voltage as well as current. So here we will get the current power. That means at the instant we can tell the power as actual power, and every 10 milliseconds back some power was there. That power we can tell it as reference power. So here we have to compare the reference power as well as actual power. If both values are same, then the error will be 0. Then no need to change the duty cycle. Then depends on the error, whether it is positive or negative. According to that, we have to increase the duty cycle as well as we have to decrease the duty cycle. So at one instant, both reference power as well as actual power will comes to 0. At that time, the duty cycle will get fixed. But here the drawback is the tracking time. That means maximum power point tracking time will be very high. Also, it can be useful up to 1 kilowatts of power only. For high power application, it's not suitable. So that's why we are moving to next algorithm that named as fuzzy logic algorithm. So the P&O algorithm does not having any memory units, but the fuzzy logic algorithm having memory units. That is the difference between the normal P&O algorithm and the fuzzy logic algorithm. So for fuzzy logic algorithm also, here we have to measure the voltage as well as current only. Voltage as well as current only, VPV as well as IPV. From this VPV and IPV, here we will get which one? Power, reference power. And the another one advantage of the fuzzy is here we can produce error as well as change in error. So according to the error and change in error, we can write the fuzzy rules. So under the fuzzy logic algorithm, it's having 5 steps. First one is pre-processing. That means error reduction as well as ripple reduction. So after finishing the pre-processing step, we will give this errors to the specification. So in the fuzzy logic, in the MATLAB, there are 2 types of tool. First one is Mamtani and another one is Sagino. For physiological algorithm, we will use Mamtani, and for ANFIS, neurophysiological algorithm, we will use Sajino. So under Mamtani, so membership function method we have to choose. So the first membership function method is triangular membership function. So triangular membership function, this triangular member, it will convert the error as well as change in error into triangular shape. Error as well as change in error into triangular shape. That means it will convert the input shape into triangular shape. Next one is rule-based engine. This rule-based engine will convert the high value of triangular signal into less than 1. High value of triangular signal into less than 1. For that only we have to write the fuzzy rules. So in the fuzzy rules, actually the error as well as change in error, we can fix the error as well as change in error. In the first error may be 0. That means if reference power and the actual power both are same, means at that time we can get error as 0. Then negative or as well as positive. In the positive, we can write the positive big, positive medium, positive small. Similarly, negative big, negative medium, and negative 0. Small, negative small. So under positive 3 cases, under negative 3 cases, including 0, totally 7 conditions. Similarly, in change in error also, in positive 3 will come, in negative 3 will come, including 0, 7. So totally 7 cross 7, 49 rules we can write it. If you omit the negative medium as well as positive medium, then you will get 5 cross 5, 25 rules. So that we can write either 25 rules as well as 49 rules. So these rules will make the high value of error into less than 1 as triangular signal. So after the rule-based engines, here we have to give to defuzzification step. Under the defuzzification, we can use maxima minima method. Through that maxima as well as minima method, we can get the original shape of the error. So the defuzzification step we are taking with the normalization. So we will get the error with less than 1 value, and the shape will be as our input error as well as change in error. Now we can give this reference signal with, we can compare the reference signal and the carrier signal. We will get a PWM pulse. We can give the pulses to the converter as well as any type of converter we can use it. Next one is the general step for the MPPT algorithm. First one is we have to start the program, then we have to initialize the E of K error as well as change in error. Then it is actually crisp shape input. So next we have to give with the falsification, and the falsification we have to use the membership function method, and the inference as well as rule-based engine will convert the high value of triangular shape into less than 1. And finally, defuzzification will convert the less than 1 into original shape of the crisp input. So according to the changes value, now we have to change the duty cycle. So under up to, if we get the error as 0, we can change the work. Actually, this is the flow diagram. So initially, here you can see we have to start the program, then we have to initialize the basic duty cycle value. After that, we have to measure the voltage as well as current. So from that, we are calculating the error. So now we have to calculate the reference power as well as we have to compare the reference as well as actual power. Similarly, reference voltage and the actual voltage, here we will get the error. If this is error to the falsification, so it will convert the error into triangular shape. Then after that, the inference engine and the rule-based engine will convert this high value of error into less than 1. Then after that, defalsification step will convert the less than 1 triangular signal into our proposed input shape of the signal. After that, we can compare the reference signal and the carrier signal. Then finally, we will get PWM pulses. Then we can apply the PWM pulses to the converter. So this is the error as well as change in error. Already I told, and I take PS, PM, and PB. PS, PM, and PB. That means positive small, positive medium, and positive big. Similarly, negative small, negative medium, and negative big. But compared to P&O algorithm, falsification is having falsification and defalsification step. So it will take more time to reach the maximum power, but we can reduce the error, power error. So next one is the PI controller based, that means closed loop based optimization algorithm. Actually here you can, here we are taking VPV as well as IPV, but for GW algorithm it's not like that. Here we will compare the reference value and the actual voltage. We will compare reference voltage as well as actual voltage, and that error is given to PI controller. In the normal PI controller, proportional plus integral controller, here also same function only. For example, if you want to maintain 300 voltage DC, reference is 300 voltage and actual it may be according to the converter output. Here we will compare the reference voltage and the actual voltage. That error is given to PI controller. Here also PI controller function is same only. We have to convert the high value of error into less than 1. For that you have to choose KP as well as KA, proportional gain and the integral gain value. So if we modify the KP and the KA value, we will get the reference signal as less than 1. Then finally we have to compare the reference signal and the carrier signal, and we will get the PWM pulse. If we give this PWM pulses to the converter, if we set 300 voltage, almost we will get the 300 volt only. But in the normal PI controller, in the control system already we have studied second order damping problem, maximum peak overshoot, rise time, fall time and settling time. This kind of problem will come. So in order to overcome those problem only, we are moving to the optimization technique. So under optimization technique, we will compare the reference voltage and the actual voltage, and then we will give this error to the optimization technique objective function, and this objective function finally it will give KP as well as KA value. If you substitute or if you replace the existing conventional normal trial and error method KP and KA value, if you substitute this value, we can reduce this kind of problem. That means rise time, settling time and fall time, steady state error problem, we can reduce it. So this is the advantages of the optimization technique. So compared to the which one, MPPT technique, global MPPT technique as well as MPPT technique, optimization is the best one for tracking the power as well as to maintain constant output voltage to the load. Then if you give this voltage to the inverter as well as grid, from my point of view, objective function based optimization technique is a good one. For a normal condition, MPPT technique is the very good one. And the next one is inverter control. So for inverter, if we give 300 voltage to the inverter will convert the 300 voltage into 230 volt AC. But in the grid, we cannot expect 230 voltage in the grid side. So we have to make the inverter output voltage with grid voltage, because in the electrical machines already we have studied about the parallel operation. Under parallel operation condition, first one is magnitude should be same, frequency should be same, and phase angle should be same. So these are the parallel operation conditions. So here we have to satisfy the real power as well as reactive power compensation problem. Now we have to know what is real power and what is reactive power. The power produced by linear element we can tell it as real power, and the nonlinear load element we can tell it as the reactive power. Simply reactive power means losses only. So from actually if the voltage is grid voltage is 230 volt, so at that time the reactive power may be zero, almost zero. So if the voltage gets reduced means the real power is reducing and reactive power gets increasing. So to calculate the power, first we have to measure the grid voltage as well as grid current. So through grid voltage and grid current, we can get the power, real power VA cos pi and reactive power VA sin pi. Now we know how much power we can give to the grid from the solar system. That one is the reference power as well as reference voltage, and here we know the actual power. We have to compare the reference power as well as actual power, as well as reference DC voltage as well as actual DC voltage. We compare these two. Here also we have to give to the PI controller, so that the PI controller will make the high value of error into less than 1. That is the reference current according to your reference power as well as reference voltage. Here we know the actual current. If we compare the reference power current as well as actual current with the help of hysteresis current controller, that is the comparator, we will get PWM pulse. If we give these PWM pulses to the inverter, we can achieve the grid synchronization. That means inverter output voltage and grid voltage will be same. So in the traditional PI controller, normal PI controller, it's produced which problem means already I told second order damping problem. So that is the main problems in the PI controller. Next one is the PMBLDC motor control. To control the PLDC motor, initially here we have to assign the reference speed and the actual speed. We have to compare these two and we will get the error. We give this error to the PI controller. Anyhow, you can keep it in mind. PI, fuzzy, ANN, ANFIS, anything, any intelligent techniques or any control technique. The function of the PI, fuzzy as well as any one of the controller is used to give high value of error into less than 1 only. The reason to generate the PWM pulse, we have to give less than 1 with signal, reference signal. That's why we are using the controller. But the PI controller may give some abnormal value between 0 to 1. But fuzzy logic controller give almost normalized value. But optimization give almost efficient value between the 0 to 1. That is the advantages of the optimized controller. So if we replace the PI controller with optimization technique, here also we can maintain good speed control. So anyhow, the reference speed and the actual speed, we are comparing. That error is given to PI controller. That PI controller output is the current. Now we can compare the actual current and the reference current with respect to hysteresis current controller. Here also we will get PWM pulse. If we use this PWM pulses to the inverter with respect to the Hall sensor position, the motor will tends to run. So next one is hardware implementation. Actually, EV means not a MATLAB simulation based one is not a good one. Here we have to compulsorily go with the hardware setup. So to develop the hardware setup, we have to control. You can think it DC to DC converter is there, inverter is there, 3-phase inverter is there. So normal DSP controller or PIC controller is not enough to generate the PWM pulse because DSP family is specially designed for our power electronics applications only. But from the DSP controller, you can generate only 6 PWM pulse. Next one is DSP, digital signal processor. In the DSP, we can generate only maximum 12 pulses plus 2 timer pulses. So the best option is pattern 6E FPGA controller. Sorry, not as pattern 6E, but FPGA controller is the good one. Field programmable gate array. So now I will explain about the hardware section, how to produce on controller. Actually, controller means microcontroller as well as digital signal processor as well as FPGA controller. All the controllers are ICs only. So it is the IC integrated circuits. So the production and the IC fabrication step, first step is silicon wafer preparation and the 6th step is the ion implementation. So from the SiO2, we will get it's we can tell it as insulator, and from the 6th step we can tell it as ion. So ion is the conductor. So if you combine the insulator plus conductor, we can tell semiconductor. So semiconductor means partially conducting device. Partially conducting device. So for partially conducting device, we have to give some cut-in voltage. At one particular voltage only, the IC will work as a conductor. That voltage we can tell it as cut-in voltage. So this cut-in voltage is defined by logic families. First, so many lot of logic families are there, but the important cases are, first one is TTL, transistor logic family, and the second one is ECL, emitter coupled logic family, and another one is the CMOS, complementary MOSFET. The microcontroller and the microprocessor comes under TTL family. That's why we are providing input voltage 5 volt. But the CMOS, the FPGA controller, comes under complementary MOSFET. Its operating voltage is 3.3 volts only. So next is the operating frequency. Depends on the operating frequency only, we can tell it as microcontroller or microprocessor. That means microprocessor can turn on one motor as well as light, but it cannot control the application because its frequency is fixed. One microprocessor operating frequency is 10 megahertz only. The frequency is 10 megahertz. From that we can calculate the timing. So T is equal to 1 by F. So 1 by 10 into 10 power 6, we will get 0.1 into 10 power minus 6 seconds. So 10 power minus 6, we can tell it as micro. That's why this controller is called a microcontroller. The for microprocessor, you can keep it in mind, the operating frequency is 10 megahertz. For DSP controller up to the microcontroller, its operating frequency 40 megahertz. PLL, phase lock loop. So through microcontroller, we can control the application also. That is the difference between the microcontroller as well as the microprocessor. So then next one is the digital signal processor. The DSP operating frequency also 40 megahertz. For FPGA controller, the operating frequency will get up to 150 megahertz. So 150 megahertz means it's too high value. So if you calculate the time, it will come nearly 10 power minus 10 seconds. So 10 power minus 10 seconds, we can tell it is VLS, a very large scale system. So the operating voltage of the FPGA controller is 3.3 volt and the operating frequency is 150 megahertz, and the total number of PWM pulses we can generate up to 100 PWM pulses. So that's why I'm suggesting FPGA controller is the best one for the EV, electric vehicle application. And okay, next one is switches selection. For switches, either we can use MOSFET as well as IGBT, but we know in the MOSFET, the switching frequency, switching losses are very low, but power losses are high. But in the IGBT, it's opposite. Switching frequency, switching losses are high, but the power losses are very less. So for small power applications, MOSFET is enough, but for high power applications, compulsorily we have to use IGBT only. For MOSFET as well as IGBT, here we have to fix the cut-in voltage. So its cut-in voltage is 15 volt PWM pulse, but from the FPGA controller, already told, we will get only how much voltage PWM, 3.3 volt PWM. But for this IGBT, we have to do 15 volt, 12 to 15 volt PWM pulse, so that we have to amplify the PWM as well as we have to separate the ground. For that, we are going with the driver circuit. So driver circuit is the combination of photodiode and phototransistor. That means simply optocoupler. So what is optocoupler means? Combination of photodiode and phototransistor. For that the transistor, we will give 15 volt from outside, and we will give the common PWM pulses to the optocoupler LED. So if we give the PWM pulses with one resistor, because LED is the current control device, so we cannot give the voltage directly. So if you connect one series resistor in series, V by R is equal to I. So the source will be now current. So if you give this pulse to the LED light will glow. It will give the lights. So this light will be a base signal for the transistor. Now the transistor will amplify the 5 volt PWM pulse to 12 to 15 volt PWM pulses. It depends on your input voltage. So now it will convert the 3.3 volt PWM into 15 volt PWM. Also you can think about the ground. For optocoupler IC input side, the ground is common, and the output we will get separate ground, so that here we can avoid the short circuit condition as well as return current problem. Otherwise our FPGA processor will get damaged because of the non-linear loads. So anyhow, the BLDC motor or induction motor or DC motor, you can use any motor, but all the motors are comes under RLE load. So we have to protect the our source controller, FPGA controller as well as microcontroller. So for that, the driver circuit will useful, very useful. So anyhow, for all the hardware development with MOSFET as well as IGBT, definitely we have to use one. Which one? Driver circuit. So for driver circuit as well as for IGBT or for FPGA controller, we have to give 5 volt as well as 12 volt or 15 volt supply. So we know our input voltage is 230 volt. So this 230 voltage is given to one step down transformer, 230 to 12 volt step down transformer. So we know transformer is a static device used to transfer the power from one circuit to another circuit. In the primary side, if you made it 230 times, and in the secondary side, if you made with 12 times, if you give 230 voltage as input, and we will get a 12 voltage as output. Now this voltage is given to the diode bridge rectifier. So the diode bridge rectifier will convert the AC voltage into DC voltage. This DC voltage is given to one voltage regulator, because VDC is equal to root 2 VAC. So if you give 12 voltage AC to the diode bridge rectifier, we will get almost 15.6 volt output. So this, but we need only 5 volt as well as 12 volt. For that, we will use regulator IC 7805 as well as 7812 or 7815 regulator. So 7805, 7 is the voltage regulator family, and 8 is the positive output. Last two digits are the output value. So from 7805, we will get 5 volt. If you use 7812 IC, we will get 12 volt. If you use 7815, we will get 15 volt output. So if we provide this voltage to the controller as well as driver circuit, we can make it as useful. So this is the one of the hardware experiment diagram, motor speed waveform. Here I am assigning 3000 RPM as reference speed. Here you can see it is the actual speed of the motor. So initially it's increasing and decreasing. After that it comes to settling. So it is the maximum peak overshoot problem. In normal PI controller, the oscillations problem will be high, but it is optimized PI controller, so we are reducing those problems. It is a small comparison between the normal converters. Actually, for boost converter, if you give 210 volt with 60% duty cycle only, we'll get a 270 volt. Then you can see the sub converter with 120 volt, we are getting 270 volt. And in the loop converter, if you give 90 volt also, we'll get a 270. In the interleaved type of converter, if you give 600 volt with a common duty cycle, we will get a 270 volt. From that, what I am telling to come means, if we reduce the number of solar panels also, we will get the same output voltage. So it is the reason why we are moving to some advanced converters. And this is the efficiency. Here you can see with the optimization technique, we are getting high efficiency. So compared to P and O, fuzzy, GWO, well optimization as well as GWO is the best one. So if you go with the hybrid optimization, still we will get high efficiency. So once again, I will recall the today's section. You can take 2 minutes rest. After that, I will recall the today's section. Okay, I will start it. So So electric vehicle. So EV is the vehicle which uses one or two electric motors for propulsion. So this is the example for the electric vehicle. That means in the electric train. So this is the common block diagram for the EV. It consists of motors as well as engine and battery, then mechanical transmission and wheel, etc. It is the common block diagram of the solar-based electric vehicle. The solar-based electric vehicle consists of, first one is the solar panel, DC to DC converters and bidirectional inverters, then chargers, then number of batteries as well as battery monitoring system. So these are the important parts of the electric vehicle. So to control the electric vehicle, the main things are the PV and the converter. PV and the converters. So here we have to choose proper converter with the MPPT algorithm. So to make the converter, so we have to give importance for the inductor as well as capacitor and diodes. So reason for choosing the motors. So general traction motors are DC series motors, DC shunt motors as well as three-phase induction motors. So these are the common motors used in the general traction motor. So first one is the series as well as shunt motor. Both the series and shunt motor, it requires a commutator, and the commutator is made up of copper segment. So it will convert the DC current into AC current, but this kind of motors need common brushes, carbon brushes. So it will increase the maintenance problems. But the one good advantage of the motor is it's a speed torque curve. So we can expect a constant speed torque curve machine. Next one is the three-phase induction motor. So the overall drawbacks of the DC motor is it needs high amount of maintenance problem, as well as it will the cost is too high. In the three-phase induction motor, stator is very good one, but rotor is very worst one. So if we combine the stator as well as DC motor, rotor with permanent magnet, we will get BMPL DC motor. So the BMPL DC motor does not having any winding in the rotor. So rotor is permanent magnet only. And without Hall sensors, we cannot run the motor. But nowadays, with sensorless operation also, we can do it with the help of vacuum of detection scheme. So this is the normal BLDC drive system. This BLDC drive system having which one means converter, boost converter, normal boost converter, but the gain of the converter is very, very low. So in order to overcome the problems only, we are going with some new converters as a big loop, interleaved loop converters, and Z source with the normal DC to DC converter. That means hybrid converters. Next one, we have to control the converters with the MPPT algorithm. So first algorithm is the P&O algorithm. It is the general algorithm, but the P&O algorithm having the drawback, we cannot use it for high power applications. Then second one is the fuzzy logic algorithm. So fuzzy logic algorithm is the good one for high power applications. In the high power applications, FLC, it's having some memory units, so that we can reduce the error as well as change in error. So last one is the optimization technique. Under the optimization technique, we can use a lot of technique, VW, well, so many things are there, Firefly, like that. So depends on the converter as well as our output grid as well as motor, we have to choose the optimization technique also. And for hardware purpose, so compulsorily you can use which one means FPGA controller only, field programmable gate array. So you can't use microcontroller for EV application, because operating frequency also very low, and the number of PWM also we can generate only 6 PWM pulse. So that FPGA controller is the best option. So if you want to reduce the number of solar panels, interleaved converter is the best one for EV, and the three-phase voltage source inverter is the good for inverter section. And for EV applications, FPGA BLDC motor, PM BLDC motor is the nice one for the electric vehicle applications. And last one is the FPGA controller is used for the total hardware implementation, and another one is the driver circuit. It is used to isolate the circuit as well as amplify the PWM pulses, 3.3 volt PWM pulses to 15 volt as well as 12 volt PWM pulses. So this is the way I am concluding. BLDC motor and FPGA controller with interleaved converters are very suitable for EV as well as electric vehicle applications. Thank you. If you have any doubt, you can ask me.
Sir, thank you, sir. Thank you for your session, sir.
Thank you.
Participants, please you can ask the queries right now. Sir is ready to ask.